Myself Supriya Anand, Assistant Professor, Department of Electronics and Communication Engineering, RIT. We shall see the experiments of Analog and Digital System Design Laboratory BECL305. In this video, we are going to test and design the Colpitts Oscillator to determine the frequency of oscillation for 100 kHz using the BJT, that is SL100. So in general, a Colpitts oscillator is a type of ELC oscillator that generates a sinusoidal waveform when it is at the high frequency. So then what do you mean by this Colpitts oscillator, or what is the input you are going to provide this? Always remember, in the crystal oscillator and the Colpitts oscillator or the RC phase shift, you are not going to provide any kind of input. Either we are going to use of the tank circuit. So here the tank circuit will be the combination of the inductor as well as the capacitor. It uses a combination of inductor, that is L, represented by L, and a capacitive voltage divider C1 and C2 to determine the frequency of oscillation. So this Colpitts oscillator shows a high frequency stability. In order to design the tank circuit, so this is the equation you need to remember, that is F naught. Frequency is equal to 1 divided by 2 pi square root of L into C equivalent. So L represents the inductive value what we are going to design for the circuit, and C equivalent is nothing but the values of the capacitor. Either you can make use of the capacitor or the variable capacitance box as well as the inductance box. So in our experiment, we are going to make use of 20k picofarad capacitance and the inductance. So here let the C1 and C2 will be equal to 0.01 microfarad. So you need to calculate the C equivalent. In order to find the frequency, you should know this equation. Mark it. F naught is equal to 1 divided by 2 pi square root of L into C equivalent, where C equivalent will be equal to C1 C2 divided by C1 plus C2. So here theoretically we are designing it over the 100 kilohertz. These are all the theoretical value, and we need to check the practical outcome. So in order to check for the practical outcome, we need to make a circuit connection as similar to the crystal oscillator. We are going to make use of the SL100, BJT SL100. Here you can observe both the R1 and R2 are similar, just like the crystal oscillator. In place of the crystal that is across the output collector, we have just replaced the tank circuit. So here tank circuit, the C1 and C2 are in parallel connection. So this is one inductance. So here this is similar to the Hartley oscillator. So in the Hartley oscillator, we are going to just replace the capacitors into the inductance, which will have the two inductance values as well as one capacitor value, which will be designed as the Hartley oscillator. Always remember, here and all, you are not going to give any kind of input. Once a circuit is designed, automatically you will get the output because of this feedback. So here the tank circuit, what we are calling, is nothing but a feedback circuit which acts as an input to this biasing, that is the base. So you are going to check the output across the CRO. So once the output is received, calculate the inductance, capacitance are fixed value. So if you don't get the proper sinusoidal wave, just adjust the capacitance value as well as the inductance value. You will get a clear sinusoidal wave across the CRO. So once you verify the values, once you receive the sinusoidal wave, observe that, calculate the time division. So calculate the time division and then calculate the overall frequency, whether it matches for the 100 kilohertz what we have designed theoretically. We'll see the circuit connection and the output. This is the circuit design for the Colpitts oscillator. As I said, there is no input for the Colpitts oscillator. The tank circuit itself acts as the feedback circuit. In order to connect for the tank circuit, we have made use of the variable inductance as well as the capacitance. The variable inductance value has been taken as 5 millihenry, and the capacitance value C1 and C2, the two capacitor, C1 is taken as 50k picofarad and C2 as 50k picofarad. Once the value has been set for this, you can observe the sine wave across the oscilloscope. Calculate the time division. Here the time division, that is of 2.4, you can observe here. From here 1 to this is 2.4.
multiply this duration, sine wave duration, with the time division. We have set the time duration as 0.1. Multiply 2.4 into 0.1 millisecond and calculate the t. After calculating the t equivalent, then calculate the frequency. We have designed the Colpitts oscillator for the frequency of 100 kilohertz theoretically. The same value has to be verified. So in order to calculate the frequency, divide the time derivation whatever you have calculated by 1. So that is 1 by t will be equal to the frequency, and verify the theoretical as well as the practical value.